Line emission spectrum. We previously looked at when solids heat up and produce incandescent light. Now we're going to look at when gases and vapors are heated up and the line emission spectrum that they produce. When vapors of elements are heated up, colors are produced. The color is determined by the emission spectrum of the element rather than the movement of the atoms and larger particles in the case of incandescence. When neon vapor is heated up, it actually produces an orange light, helium produces yellow, and mercury produces a blue light. So it doesn't matter how much you heat it up, those gases will always produce that color of light. Now these emissions cannot be produced in solids, only gases. So gases are considered simple single molecules or atoms moving at high speeds in random motion. But the spectrum that's produced is not continuous like it is in solids. It has distinct frequencies. When we pass this light through a diffraction grating, we can actually see what these frequencies are. And what this means is that these frequencies are properties of the atom themselves rather than the temperature of the material. The image on the screen is an example of neon glowing orange, and the emission spectrum that's produced appears like this. So there is some infrared light that's produced, some ultraviolet light that's produced, but in the visible range, which our eyes can detect, this light is produced, and when you mix those distinct frequencies together, it appears this orange color to our eyes. So just a bit of a revision, a spectroscope is used to break down those colors with a diffraction grating, and depending on the frequency of light, each distinct frequency will diffract at a different angle and reinforce at a different angle on the screen, so you can easily see the different frequencies that the light is comprised of. So a continuous spectrum with every single frequency on there in the visible range might look like this. The emission spectrum of a gas might look like this. Okay, we have some examples here. Although these spectrum are comprised of different frequencies, when we look at the light source itself, all those frequencies are hitting our eyes at the same time and producing a certain color that we can see. It's just like when we see a continuous spectrum all at the same time, we see it as white. It has been found that the line emission spectrum for each element is unique. The frequencies of light emitted by each are all different. Using this knowledge, we can identify what element exists in a light source by matching the position and hence the wavelength of the emitted light in the line spectrum of an unknown gas. Now, this spectrum is actually due to the moving of electrons between different energy levels in the atom. Now, in chemistry, these energy levels are called electron shells. And when an electron moves between energy levels, a photon of light is released. And this photon matches perfectly that transition between energy levels, which gives that specific frequency for that particular element. Another way that energy levels can be drawn is like this. So we have our ground state energy level that electrons want to be at. When an electron is provided with enough energy, it has enough energy to leave the electrostatic attraction to the nucleus, and at this infinite energy level, it leaves the atom and no longer belongs to the material. And we can see here that the energy levels are not equally spaced. There's a large gap in the first energy level to the second, and then they get closer and closer in this region, and there's an infinite number of energy levels there. And important things to note here is the value of the energy levels that are written here. And what this negative 13.6 electron volts indicates is that if there was an electron at this energy level, it would require 13.6 electron volts of energy to leave the material. And it is written as a negative is because energy has to be put in to make that electron leave. So if an electron jumps up a level or comes down a level, the energy of that photon that's released can be calculated using this formula, where the energy of the photon is related to Planck's constant and the frequency of the photon. And you can see in this example here that we have an electron that's moved from energy level 2 back down to the ground state energy level 1, and a photon is released. The change in energy level is about 10.2 electron volts. So that photon would have 10.2 electron volts worth of energy, and using the formula on the previous page, we can actually calculate the frequency or even possibly the color of that light if it's in the visible range. So the movement of electrons between energy levels is also why we see these characteristic peaks on X-ray diagrams. They correspond to the discrete energy level transition within atoms of a target material. Explain why line emission spectra are seen when elements that are in a gaseous state are heated up.